Greetings. Welcome to Electronic Circuits 1. I am Razavi, and this is lecture number 25. Today we will talk about the sensitivity problem in the common emitter stage and see how degeneration helps with that sensitivity. And then we will look at another flavor of the CE stage that also has better properties in terms of sensitivities to supply and other parameters. Before we go there, though, let's briefly look at what we covered last time. So in lecture number 24, we started creating a simple biasing network for the common emitter stage, saying that we need a certain base emitter voltage, about 0.8 volts, and that can be created by a resistive divider that is connected to the supply voltage. The supply voltage is this VCC, and is connected to the voltage divider. And so instead of using a battery for every stage of every amplifier, we decided to use a simple divider. Now, the problem was that we noticed if, for example, the supply goes up by 5%, and therefore this base voltage goes up by 5%, then we see that the collector current changes by a very large amount, for example, by a factor of 4.65. So that is the principal issue in this type of biasing circuit. If you recall also, we said that to minimize the sensitivity of this voltage to the base current, meaning to the beta, we prefer to use a large current here, about 10 times the base current, so that the sensitivity, at least to beta, is minimized. But the sensitivity to VCC is still there. Okay, so then we thought maybe if we add a degeneration to the emitter, that will help with the supply sensitivity as well. Previously, we considered emitter degeneration for other sensitivity issues, such as variation of IC with temperature or with the signal level, etc., but we are thinking maybe it also helps here. Now, we had a clue last lecture as to why it should help, and the clue came from the observation that if the base voltage of this device goes up by some amount, then the emitter voltage also has to go up. Maybe not by the same amount, but to some extent. And we prove this by contradiction. So we see that if the base voltage goes up by, for example, 40 millivolts, as we had last time, and the emitter also goes up by some amount, then the base emitter voltage does not go up by 40 millivolts, which means the collector current does not increase by such a large factor. So intuitively, we think that having this resistor here helps with the suppression with reducing the sensitivity to the supply voltage. So today we'll try to quantify this effect and see exactly how and under what conditions we have less sensitivity to supply, meaning we don't get so much current variation when the supply goes up by, for example, 5%. All right, so today we will look at that, and then we'll go over a design example, and then we'll go to a new stage called the self-biased stage, which also has some good properties. All right, so let's look at this circuit again, and again I would like to see if the base voltage goes up by delta V, how much does the emitter voltage go up by? If it goes up, if it doesn't go up at all, then this is no better than having no degeneration. But last time we proved intuitively that the emitter should go up. The only question is by how much. Okay, so how do we analyze this? Here's the circuit in its simplest form. So let's write this as sensitivity to Vx change. So we want to see if the supply changes, and therefore Vx changes, how much this collector changes, collector current changes by. All right, so what we will do first is we would like to see how much this voltage changes by. And let's assume that the change that comes here is not that large. If I have a small change at the base and I would like to find the change at the emitter, maybe I can just draw the small signal model of the circuit and analyze it, because the small signal model exactly represents a change in this voltage, a change in this voltage, etc. So let's do that. Let's draw the small signal model of the basic circuit by itself without R1 and R2. So here's what we have, R pi with a voltage of V pi on it. Then we have GM V pi. We have a resistor RC. I modeled this change in the voltage by some voltage source, AC small signal voltage source. So we can call it whatever we want. Maybe we'll call this Vx. Vx represents the change in this voltage. And we have a resistor that goes from the emitter to ground, Re. And what we are interested in is the change in this voltage. So again, we will call this voltage Ve, the small signal change. All right, so we know that for a given change here, if this Vx is some voltage swing, then this is not zero. For example, if this voltage goes up, this voltage also goes up. We are trying to see how much the voltage changes at this point. Okay, how do we analyze this? That's not that hard, given that we have VE from the top terminal of RE with respect to ground. So that means that this current is equal to VE over RE. Okay, that was easy. Again, remember that we need to eliminate V pi because we are interested in VE in terms of Vx. All right, so what else can we say? Well, let's write a KVL around this loop. KVL says that this voltage is equal to this voltage plus this voltage. So we have Vx is equal to V pi plus VE, the emitter voltage, right? So we found V pi. V pi is equal to Vx minus VE. All right, so we wrote Ohm's law here. We wrote a KVL here. Now we're going to write a KCL at this node. The current coming down R pi plus this current should be equal to this current. So let's do that. The coming down R pi is V pi over R pi. But we have V pi. So we will write V pi, Vx minus VE, divided by R pi, that is this current, plus Gm times V pi, plus Gm times V pi, which is again Vx minus VE over R pi. Oh, I'm sorry, no, that's wrong. I just need to write Gm times V pi. So Gm times Vx minus VE, that's that current. These two currents have to add up to this current. So that's equal to VE over RE. So that was easy. We have VE and Vx. We can find VE over Vx. That would be the ratio, the change as it goes from here to here. Okay, so let's do that. We have, we factor Vx, keep it on this side, Vx over R pi, or maybe I just do this, factor Vx out to make it a quicker calculation, 1 over R pi here. Then we have Gm, and on the other side we have VE. We have 1 over RE plus 1 over R pi plus GM. So now we can find VE over Vx. VE over Vx. So how much is that? Well, you just need to multiply by R pi times RE, both sides, and then remember that GM R pi is equal to beta. So this will give us something like this, RE over 1 over GM plus RE. In going from here to here, I have recognized that GM R pi is beta, and I have assumed that beta plus 1 is approximately equal to beta, like what we did for the common emitter stage with degeneration. Remember, when we calculated the voltage gain of the stage, we had to make those approximations. So it's the same thing here. Okay, so this says that for a given change in X, we have a certain change in E, in the emitter voltage, which is less than the base voltage change. This is less than 1. We can define this as a voltage gain if you want. So the gain from here to here, the gain from here to here. If it changes by 40 millivolts, how much does it change by? Well, it changes by less than 40 millivolts, and that depends on how these two values compare. If it just happens that 1 over GM is much less than RE, then this is close to 1. So a change here will create approximately the same change here, right? That means that the base emitter voltage doesn't change much. This is the key point behind the circuit. We want the base emitter voltage not to change much. Because last time, when we changed the base emitter voltage by 40 millivolts, we had a factor of 4.65 change in the collector current, right? So we want the base emitter voltage not to change much. And that can happen if when the base goes up by 40 millivolts, the emitter also goes up by close to 40 millivolts. And this says, for that to happen, we should have 1 over GM to be much less than RE. So we write this. If it just happens that 1 over GM is much less than RE, then VE, the small signal change in VE, is approximately equal to Vx, and that means VBE changes by only a small amount. Okay, so that's the key idea behind how degeneration helps with reducing supply sensitivity. If the supply goes up by 5%, Vx goes up by 5%, for example, 40 millivolts. Then this point also goes up by something, maybe 30 millivolts, maybe 40 millivolts, which means the base emitter voltage does not go up by 40 millivolts. And that means that this collector current does not change as much as it did last time. And that's the idea. Okay, so we can write this in a slightly different form. We see that here, 1 over GM is equal to VT over IC. IC, the bias collector current. So we have RE times IC much greater than VT. These are equivalent conditions. So that's a good way to remember this. The DC voltage drop across RE, this much, must be much greater than 26 millivolts for this to be negligible with respect to this, so that when the base voltage goes up as a result of supply change, the emitter goes up by approximately the same amount, and therefore the base emitter voltage does not change much. And therefore the collector current does not change much. So that's how we view this. And interestingly, and not very coincidentally, this equation is the same as what we had before for the gain of the stage. If you remember, the gain of the stage was reduced to minus RC over RE in the special case when this condition held. So these are very related, and that's what we get in this case. All right, so it's good to remember this relation whenever we want to analyze and optimize this biasing circuit. Let me take a look here and see what we need to do. All right, so let's go ahead and summarize everything we have learned about biasing here. So, summary of biasing. Okay, so we said that we choose the current flowing through R1 and R2 to be much greater than the base current, so as to minimize sensitivity to the beta of the transistor. So we say VCC, this voltage, divided by R1 plus R2 should be about 10 times the base current. Okay, so that if the base current changes by maybe 30%, 40%, the voltage at this point doesn't change much. It's still given by the division between R1 and R2. All right, what else do we know? Well, we decided that the voltage across RE has to be some reasonable amount. Now, maybe we can make it 10 times VT, maybe not, but RE times IC must be much greater than VT. I wrote this in parentheses because sometimes the design doesn't allow us to do that, but preferably we would like it to be maybe 200 millivolts, maybe 300 millivolts. Okay, now there's one other component that we haven't quite discussed, and we need to get that under control, and that's the value of this RC. How do we choose RC? Well, remember that the voltage gain is proportional to RC. So to maximize the gain, we would like to maximize RC. But do we have infinite room for that? No. What we know is that for a given bias current in the collector, as RC increases, the DC voltage here decreases. It comes down, right? So we know that if I call this node C, the collector voltage, VC is equal to VCC minus RC times IC. RC IC is the voltage drop across this resistor. We subtract it from the supply, we get the collector voltage. Collector voltage with respect to ground. Okay, how low can this guy go as I keep increasing RC? Well, we would like this voltage, the collector voltage, to be around the base voltage or higher, no lower, because we enter saturation. So this is another important guideline that we have to remember. This should be greater than or equal to Vx. So whatever we choose for Vx, we have to choose RC to satisfy this equation, and that gives us an upper bound for RC. All right, and that's how this whole circuit is designed. All right, to hammer these in, let's go and take a look at an example with some numbers to see how things come out. So here's an example. So let's change the color of our pen to red. Okay, so here are some numbers. Suppose that we have a supply voltage of 1.5 volts. And we are given a power budget of 1.5 milliwatts for this amplifier. P is equal to 1.5 milliwatts. As you know, power consumption is a critical component in many electronic devices, especially portable devices. As you can see from your mobile phone, you have to charge it at the end of the day, you have to charge it every 2 days. That all depends on how power hungry the circuitry inside that mobile phone is. All right, so 1.5 milliwatts, that's our power budget for this little circuit. And then, for example, beta is 100 for the transistor. That's probably good enough for now. Okay, so with these basic numbers, we want to start designing the circuit. All right, from the supply voltage and the power budget, we can find the total current that we can draw from the supply. Because we know that the total current from the supply, we'll write it as I supply, but sometimes we also write it as ICC, just like VCC, and that would be equal to VCC over the power budget. So that's 1 milliamp. If we continuously draw 1 milliamp from the battery, the power consumption is 1 milliwatt, 1.5 milliwatts. Okay. All right, so the total current that we can draw from the battery is 1 milliampere. Where does it go? Well, hopefully most of it goes this way, and a small fraction of it goes through these two resistors. So for now, let's neglect the current that flows through these resistors and allocate this entire budget to the collector. So we say IC is approximately equal to 1 milliamp. Why do we do this? Well, for simplicity. At the end, we can come back and adjust the numbers a little bit. But if at this point we say, well, we have no idea where do we start, what equations do we write, that's a little cumbersome. So we make this assumption and hope that the assumption is reasonable at the end. Okay, so that is the collector current that we have. How much is the base current? 1 over beta times that. So we see that base current is equal to 10 microamps. How do we choose this current? 10 times that. So we say VCC over R1 plus R2 equals 100 microamps. Right? Because if the base is 10 microamps, I want that to be sufficiently larger. Now, right here, we can see if our first assumption was good. We said all of the collector current, all of this 1 milliamp can go to the collector. Well, we're consuming 10% more power through this than what was given to us. Right? We had a total budget of 1 milliamp. We have already consumed 1 milliamp in the collector and then 0.1 milliamp in the resistive divider. So yeah, maybe that's not very good. You can always go back and change these a little bit, but that'll do for now. Okay, so that is to ensure that the base current has negligible effect on this voltage. We have one more equation. Well, first we have to decide how much drop we want to have across RE. Remember, this is the drop across RE. So let's pick a number. How much? It's okay, we just pick a number and go with it and see what happens. We're just exploring. The circuit won't bite. So let's just pick a number. Pick RE IC equals 100 millivolts. It's not really much greater than VT. It's about 4 VT, but that's okay. We just use this, do the calculations, go to the end, look at the results. Are the results adequate? Do they satisfy our needs or not? If not, we come back and readjust. But at the beginning, if we are overwhelmed by all this information, we just don't know where to start. Okay. So because IC is 1 milliamp and this drop is 100 millivolts, we end up with RE equals 100 ohms. So far so good. We have this drop, we have the current through these resistors, and we still need to find R1 and R2. Okay, well, if this voltage is 100 millivolts, and this voltage is about 800 millivolts, approximately, right? Then Vx with respect to ground is 0.9 volts. So we say Vx is equal to VBE plus 100 millivolts. This voltage plus this voltage. So that's about 0.9 volts, right? And this voltage is produced by this divider. So that should be approximately equal to R2 over R1 plus R2 times VCC. So now we have two equations and two unknowns, namely R1 and R2. So let me change the color of my pen. So from this equation and this equation, I can find R1 and R2. So it turns out that these will give us R1 is equal to 9 kilo ohms and R2 is equal to 6 kilo ohms. All right, so let me double check to make sure I got my numbers right. Okay, very good. What else do we need to do? Well, we need to find the collector resistor. We said that we have this limitation. This voltage that you see here cannot be too low. So let's go ahead and do that. All right, so we say VC, the collector voltage, is equal to VCC minus RCIC. So VCC minus RCIC. And this should be no less than this voltage to make sure that this junction doesn't get forward biased. And we know that Vx is 0.9 volts. So this is 0.9 volts. This should be IC. So that's easy. 1.5 volts here, 0.9 volts here. IC is 1 milliamp. We can find RC. So that gives us RC equals 600 ohms. So that's all we have. That was easy. Okay. All right, we found these values, and now I have a little quiz for you. So here's our quiz of the day. It has two parts. Calculate the gain of the amplifier and how do we increase the gain without changing the bias components. All right, I'll give you 90 seconds to think about that. All right, so what did you get for the gain? Well, remember the gain equation for the common emitter stage with degeneration. So we have AV is equal to minus RC over total resistance in the collector divided by 1 over GM plus all of the resistance seen tied between the emitter and ground, so RE. So RC is 600 ohms, 1 over GM is 26 ohms at 1 milliamp of bias current, and RE is 100 ohms. So that gives us a gain of minus 4.76. That's not a whole lot of gain. Remember that for the basic common emitter stage we calculated a long time ago, we had a voltage gain of 30 or 40 or something, but now it dropped to less than 5. Okay, so how do we increase the voltage gain of the circuit if we don't want to touch these resistors and the current and anything else? That sounds like impossible. Well, it's not impossible, but it has some limitations. So the answer is the following. So this is the answer to A. The answer to B is this. This amplifier is used to amplify a signal, right? And the signal has some frequency content in it, some frequency components. For example, human voice has a range of 20 hertz to 20 kilohertz. If you have a video signal, the video signal that this camera is capturing right now has about 5 megahertz of bandwidth. Goes up to 5 megahertz. Well, this is a high definition camera, so maybe a little more. So, the point is that when the signal comes in, it's an AC signal. It's not DC. If it's an AC signal, we want to increase the gain of the circuit for AC signals. We don't have to increase it for DC. So when we think of AC, we are thinking maybe, if I look at this equation, I can increase this gain by trying to decrease RE for signals, not for DC, but for signals. So how can I reduce RE for signal frequencies that come into the circuit? Well, we know a device whose impedance goes down as the frequency goes up, and that's a capacitor. A capacitor is an open circuit as far as DC is concerned. So for bias calculations, we don't worry about it, it's not there. But when the signal comes in, the capacitor has a low impedance, could have a low impedance. So if I place a capacitor in parallel with RE, then the result can be small, can be smaller than RE for some frequencies. And for those frequencies, this gain will be higher than the number that we have right now. So that's the basic idea. So let me draw that circuit here and show you how that would be done. We have RE to ground and we place a capacitor in parallel with RE. Let's call that CE. For example, suppose CE is a good short circuit at the frequency of interest. If it's a good short circuit, then the impedance that we have between the emitter and ground, and AC ground, is close to 0. If it's close to 0, we can take this away. And the gain goes back to minus GM times RC. So ideally, maybe not practically, but ideally, what we want is 1 over CES, CE omega, should be small for the frequencies of interest. Now, sometimes that's possible, sometimes it's not possible, but that's the idea. So if for the frequency range of interest we can have a reasonable value for this capacitor, then that capacitor provides a somewhat of a short circuit, reduces this impedance, which means what goes in here is no longer RE, but RE in parallel with this capacitor. So the overall gain will be higher. And that's how we can do that. So in some applications, that's possible. In some applications, not, because we end up with a very large capacitor. But that was one point of curiosity that I wanted to impart to you. Very well. Regarding this circuit that we analyzed and this example, let's take a step back and see whether we have actually gained anything. We said, I advertised, that degeneration helps with supply sensitivity. The question is, in this example, where I chose the drop across RE to be 100 millivolts, well, that's the idea, that's what we wanted really, but we couldn't do that for various reasons, so we chose to be only 100 millivolts. Do we have better supply sensitivity, meaning lower supply sensitivity, than before, when we had no resistor here at all? So because we have some numbers, we should be able to calculate if the supply goes up by 5%, what happens to the collector current, right? And then see, in the previous example from last time, when the supply went up by 5%, the collector current went up by a factor of 4.65. It was multiplied by 4.65. The question is, if I have this modest drop of 100 millivolts, will the current change be much less than that amount? So let's try that. Okay, so let me show you the procedure, and then I'll go to the next page and I'll try to implement it. The procedure is as follows. We assume that this voltage goes up by 5%, just like before. All right. So this voltage is 0.9 volts presently. If you remember, 0.9 volts. So when the supply goes up by 5%, this 0.9 volts goes up by 5%. So that would be 45 millivolts, right? So we take this 45 millivolts, and we would like to see how much of it appears here. All right. So how much of it appears here? Well, we have a calculation before. It says if Vx, the change in Vx is 45 millivolts, the change in V is given by this. We have RE, 100 ohms. We have 1 over GM, 26 ohms. We can calculate that. All right, so far so good? Are you with me? Okay, so I said, if this goes up by 5%, 45 millivolts, then I can figure out how much this goes up by from this equation. By some amount, maybe less than 45 millivolts, right? Because this is less than 1. All right. Now I have the change here. What do I do with that? Well, if I know how much the emitter voltage changed, I know how much this current changed, right? I just divide 45 millivolts, that voltage change here by RE, that gives me the current change. And that current change is the collector current change. And then I can see how bad the situation is. So again, a quick summary. This goes up by 5%, 45 millivolts. This goes up by some amount. We can calculate from here. We divide that by RE. That gives us the change in the collector current. And then we'll see. So let's do that. Let's go to the next page and see what we get when we include these numbers. Okay, so Vx is 45 millivolts. 5% change. So little Vx indicates the change in big Vx, right? Okay, so Ve, the change in the emitter voltage, is equal to Rs divided by 1 over Gm plus Rs times 45 millivolts. Okay, and that gives us 36 millivolts. So this is 36 millivolts. We have 100 divided by 126, and that's what we get. All right, 36 millivolts. This is the voltage change at the emitter, or the voltage change across the emitter resistor. So we can say that change in emitter, which is the same as collector current, is equal to 36 millivolts divided by 100 ohms, because RE was 100 ohms. So that's 0.36 milliamperes. Is that a lot? It is actually somewhat a lot, yes. So the current was 1 milliamp, and now it has gone up to 1.36 milliamps. So on an absolute scale, it's still not very good. But compare that with what we had last time. Last time, as a result of 5% change on the supply, we saw that the collector current changed by a factor of 4.65. So 465%. Now we have a change of 36%. So even though the drop across RE is only 100 millivolts, it dramatically reduced the sensitivity of the collector current to the supply voltage. All right, so that was that quick example, and we are now ready to move to another circuit. Okay, the next circuit that we will study is called the self-biased common emitter stage. So self-biased CE stage. All right, so as usual, we know a common emitter stage has an input applied to the base, has an output sensed at the collector, and then some resistor at the collector. So the basic stuff is still there. All of those are still here. The emitter goes to ground. We have our output here, power supply connected up here. And we still need to bias the base, right? The base has to have the right voltage with respect to emitter. So this time, instead of a divider, what we do is we connect a resistor from the collector to the base. I'm going to call that RF. Interesting and strange. Okay, so what exactly happens now that we don't have that voltage divider, but instead we have RF? Well, qualitatively, we can make a quick observation. We can see that this circuit also has a low sensitivity to VCC. If VCC changes by 5%, the collector current will not change by that factor of 4.65. So let's see why that is, okay? All right, so let me change the color of my pen to brown. All right, so let's say VCC changes by 5%, okay? So 5%. Now, you might say, well, if this side changes by 5%, this side probably changes by 5% too. That's what we said about the resistive divider, right? Okay, well, maybe, but let's think of it this way. If this point wants to go up by as much as 5%, then it also wants to change the base voltage. So if this voltage goes up, as a result of supply change, then the base voltage goes up through this resistor. If the base voltage goes up, what happens to the collector current? The collector current increases. If the collector current increases, what happens to this voltage? This voltage wants to decrease. Remember, we have inversion. When the base voltage goes up, the collector voltage goes down. So there's a self-correction mechanism in the circuit. Supply goes up by 5%. This wants to go up by 5%, but it doesn't, because if it goes up, then it raises the base voltage. The base voltage raises the collector current. The collector current wants to reduce that voltage. So that's why we call this a self-biased stage. So we say changes in VCC are counter acted by Q1, Q1 being this transistor. And this is because we have this path here. Sometime in your future, you will learn about feedback, negative feedback, and this resistor actually creates negative feedback from the collector to the base. But for now, we don't worry about it here. All right, so that's an interesting observation. Qualitatively, we feel that this circuit also has a reasonable supply insensitivity. Now, the next observation is the following. So that was one observation. The next observation is also interesting. In this circuit, we can write the base voltage, just DC for bias conditions, and see what we get. We can see that VB, the base voltage, is equal to the collector voltage, this voltage, minus this drop. There's a drop from here to here. Why? Because the base current of the circuit has to come from RF. Doesn't have anywhere else to come from, so it has to come from RF. So the collector current flows this way, the base current flows this way, generating a voltage drop of IB times RF. So minus IB times RF. So we start with a certain voltage here, and we lose a certain amount, IBRF, before we get to the base. That much. This says that the base voltage is always less than the collector voltage. Why is that good? It's good because it guarantees that this device does not go into saturation. For saturation to happen, the collector voltage should dip below the base, but this doesn't allow it. So we say Q1 does not saturate, right, because of this property. So that's also a useful property. We did not have this in the simple common emitter stage with resistive divider connected to the base, right? This is different. Okay. So now, for this contraption, we are still interested to find the collector current, the bias current, if we know all these things, the resistor and the resistors and the beta, etc., right? So let's do that. So let's calculate the collector bias current. That's always necessary because the collector bias current gives us the GM and RO and RPi and everything else. So we do need to calculate it. All right, well, how do we go about doing that? Well, I will make one approximation. I will approximate IB to be much less than IC. And that's usually true because beta is large, right? So beta is much greater than 1, which means IB is much less than IC. So if that's true, I can say that IC in its entirety flows through RC, meaning that the little fraction that we lose to the base is negligible. So if all of IC flows through RC, the voltage drop across RC is IC times RC. So we have a current of IC flowing here because we are neglecting this base current contribution. And that tells us that we have this voltage here is equal to VCC minus RC-IC. All right, the supply voltage minus RC-IC gives us this voltage with respect to ground. Okay, so I'm still trying to find IC. Now, I will go this way. I will say, I know the voltage here, and I have a certain drop across this resistor equal to RF times IB. So that gives me the base emitter voltage. So I can write VC minus RC-IC, that is the VCC, that's the collector voltage, minus the drop across the resistor, minus RF times IB is equal to the base emitter voltage, right? So that's the base emitter voltage. And I know that IB is just 1 over beta times IC. So this is IC over beta. Okay, so if I want to find, for example, IC as a rough approximation, this is what I would do. I would say, well, VB is about 0.8 volts, and I have RF, I have RC, I have VCC, I can quickly find IC. That would be a first approximation. Now, if you say, well, I don't know exactly VBE, because it depends on things. It might be 750 millivolts, 800 millivolts, etc. No problem. Then we'll also write VBE is equal to VT log of IC over IS. And now we iterate. We make a guess for IC, just the way I mentioned before. Plug it in here, we find a new VBE. From the new VBE, we find a new IC. We plug it back in here and continue until IC converges to some constant value. So we can easily calculate and find the collector current. Once we have the collector current, we have everything else. We have the drop across this, we have the voltage here, we have the base emitter voltage, and everything else. So now the circuit is completely analyzed and ready to go. All right. So let's try to continue with this equation for now. And what we can do is, because we have this equation, we can quickly find IC in this form. So if I assume VBE is relatively constant and well known, I can rewrite this equation in the form of VCC minus VBE divided by RC plus RF over beta, right? RC, there's a negative here, there's a negative here. So RF over beta plus RC, and that VCC minus VBE. So this is a quick estimate, assuming that VBE is relatively known to some approximation. All right, so this equation says that if we want to minimize the sensitivity to beta variations, we should make this component much less than RC. So to minimize sensitivity to beta, we choose RC to be much less than, much greater than RF over beta. So in other words, RF is chosen to be much less than beta times RC. Okay, so that's one little rule of thumb to remember about how these values are chosen. Now, whether we can always do this or not, we don't know, but that's something good to remember. Okay? All right, so that's one condition. Let's see. What else? Okay, so one other interesting observation I can make here is as follows. So that's one observation. Second observation. If VCC goes up by 5%, so that's our usual test of supply voltage variation and then how much the collector current varies. If VCC goes up by 5% here, this amount, what happens to the collector current? Well, let's look at this equation for now. VBE doesn't change much, right? Because VBE is, let's assume VBE doesn't change much and proceed and see what happens. If VBE doesn't change much and VCC changes by 5%, the worst case is that this entire numerator increases by 5%. Right? It will be less, But let's say VCC is so large, maybe 5 volts or 10 volts, and when it changes by 5%, the numerator, in the worst case, increases by 5%. Then what happens to IC? IC, because these are constant, IC increases by 5%. So we can see that if VCC goes up by 5%, IC goes up by about 5%. That's very interesting. In the first common emitter stage, with resistive divider to connect the base, we saw that when the base voltage goes up by 5%, the current goes up by a factor of 465%. In the second case, with emitter degeneration and the 100 millivolt drop across the emitter resistor, we saw that when the supply goes up by 5%, the current goes up by 36%. Now here, when the supply goes up by 5%, the current goes up by 5%. That's very respectable. Now, let's go back and check one quick assumption. I said VBE doesn't change much. Is that true? Well, if IC changes by 5%, VBE doesn't change much. That's correct, right? If IC changes by 5%, VBE will change by a very small amount because there's a log relationship here. So that makes sense. So this tells us how good the circuit is in terms of resisting supply variations. And that's sometimes we use the circuit in analog design. Okay, let's go through a quick example with numbers just to get comfortable with this self-bias stage. So I'll change the color. So example. So again, VCC is 1.5 volts. IC is 1 milliamp. Beta is 100. IC is 1 milliamp because power budget is 1.5 milliwatts. And beta is 100. And we would like to see how the circuit comes about. Okay. Well, what parameters do I have to choose? I have RC and I have RF, really, not much else. How much do I choose for RC? I think that this voltage is 1.5 volts. How much is this voltage? This voltage is about 0.8, maybe 0.9 volts, right? Because we have 0.8 here, and we have some drop across this resistor, but probably not much. So again, we can make an assumption, proceed, and at the end check our assumption and see how bad it is, right? Okay, so let's say that this voltage is not that far from this voltage, maybe a little higher. So maybe this voltage is 0.9 volts, right? 0.8, 0.9, something in that range. So I'm thinking that VC is about 0.8 volts, maybe 0.9 volts, because we do have some drop across RF, 0.9 volts. So that means that we have a voltage drop of 1.5 minus 0.9 across RC. So RC is given by 1.5 volts for the supply, minus 0.9 volts, because that's what we have at the collector, that's our guess, divided by the collector current, 1 milliamp. And that happens to be 600 ohms. Right? We have 0.6 here, 600 ohms. Okay. All right. How about RF? How do I choose RF? Well, we had some sort of prescription for RF. We said RF should be much less than beta RC. So we choose RF to be approximately equal to beta RC divided by 10, because we want it to be much less. So that's 600 times 100 divided by 10, so that gives us 6 kilo ohms. Okay, 6 kilo ohms. Now let's do a quick check. I assumed that the collector voltage is 0.9 volts. Is that close to what we want or not? Well, RF is 6 kilo ohms. The base current is about 10 microamps. The base current is about 10 microamps because the collector current is 1 milliamp, right? And the beta is 100. So that means that the drop across RF is 10 microamps times 6 kilo ohms. So drop on RF is equal to 10 microamps times 6 kilo ohms. That is 60 millivolts, right? So is that correct? 10 to the minus 3, 10 to the minus 6. So that's 10 to the minus 10 to the minus 3, 10 to the 3, 10 to the minus 6. That's 10 to the minus 3. 600 times, yes, that's 60 millivolts. So that's not far from what we expected, and we assumed about 100 millivolts because we thought this is 0.8, this is 0.9. So that's not too bad compared to our original assumption. Very well, this gives us a quick procedure for calculating the parameters in the self-bias stage. Now, we have a resistor connected from the collector to the base. This resistor does all sorts of interesting things. For example, what is the input impedance of the circuit? RF is no longer in parallel with something, right? R pi goes from here to here. RF goes from the collector to the base. So that's not in parallel with anything. How much is the output impedance? The output impedance looking this way is no longer RC. There's some stuff going on here. Very interesting. But these are things that we typically defer to more advanced courses, and we don't deal with them here. All right, our time is up. I will see you next time.